Hi everyone, and welcome to the video on section 2.4. So in this section we're going to be talking about continuity. So the definition's right here. Right above that you should read through that short paragraph that talks about what specific things you should be thinking about when going through the section. But we're just going to dive right into the definition here. So definition says a function f is continuous at a number a if, and then gives this little formula here, the limit as x approaches a of our function is equal to f of a. So, what is continuity, this seemingly new idea? Well, it's not really new. It's just limits, like we've been dealing with them, except before with limits, we didn't care what happened at the actual point, right? Remember, we had here this value a that we were approaching, and all we cared about for the limit was, okay, as you get close to a on the horizontal, what's the function do? Does the function seem from both sides to be approaching the same number? And if that was true, you had a limit, we were done. All we're saying now is all of that still all of that. We want our function from both sides to be approaching the same number, but also, so this is important, this idea of continuity being continuous, this is limits, the idea of limits, plus now this extra condition. Plus, we also want to make sure the function's defined there, and that value, when we plug a into the function, we actually get the same thing as the limit. So it's an additional thing. So you should think of continuity as like, okay, there's a limit and we also need the function defined and equal. So what we're going to do here is rely on the work we've done with limits and then just have something extra to check. So it's just an additional thing. Okay? And the way that we're going to rely on limits is by noticing that this definition kind of has a lot to it, and it can be broken down into three pieces. So that's right here, these three pieces. Okay? So if you are continuous, then there's a checklist. So we can think of this as a little checklist, and we're going to use it as that. Okay? We're going to use this in some of the examples. If you're continuous, then first of all, the function needs to be defined there. Number one. Number two, at that value, the limit has to exist. Okay, that's number two. And number three, they have to be equal. Now here's the thing. To be continuous at a, all three need to check out. Right? So in order to be continuous, we need all three. So what you should be doing whenever you learn something like this, like something to be true, you need this checklist of things or these conditions. Then for it to not be true, if I need three things to be true, then to not be true, I just need one of them to fail. So that's something you can always try thinking about right after you learn something new. Just go opposite, like, okay, this definition needs three things. Well, what does it mean if this definition doesn't hold? Then what? Well, what that means is we just need to break one. So to be, and this is a word that is described just below, but I'm going to just use it now. Discontinuous. We don't say not continuous, we say discontinuous. So to be discontinuous at a, we need to break at least one of these three. Not all of them necessarily. We could break all three, but we just need at least one. As soon as you go through that list and you're like, oh, number 2's not right, you're done. Not continuous. Discontinuous. Oh, number 1 works out. Number 2 works out. Oh, but number 3 doesn't. Discontinuous. That's the way that you can talk and think about not being continuous. If you're continuous, though, we need all three. So for continuous, we need all three. To be discontinuous, we just need to break one of these. So that'll come up later. Okay. The last thing that's just a little technical of a thing, but it's useful to mention, is with this idea of being discontinuous at a point. We don't want to consider points that the function doesn't really have anything to do with. So what do I mean by that? Just, it's here, and I'll say it, but as a picture, let's say I have this function that's defined like this. Okay, so we can go through all the points it's defined at. All right, maybe it goes on forever. We can go through and look at all these points it's defined at, and we can go through and be like, oh, continuous, discontinuous, continuous, discontinuous, right? We can go, okay, here's A, and my continuous, discontinuous, and we could go practice all that. But what we don't want to do is start looking at an A over here and start thinking about this idea. Because where's the function, right? Where's the function here? It's not defined at this value. It's not defined anywhere near it. So we don't even want to talk about continuity because this function has nothing to do with this value or anything near it. So not only does it not make sense to talk about f of A for that A all the way to the left, it doesn't make sense to talk about the limit because the function's not even defined near A. So none of them make sense to talk about, right? So this side wouldn't make sense to talk about of the equation. This side doesn't make sense to talk about. And so we don't even define continuity, discontinuity for points over here. We're just going to stick to points in the domain, okay, or points that might just be one point not in the domain, like an asymptote, a hole, things like that. That's where the discontinuous is really kind of coming in. It's pointed at holes, or what's called a removable discontinuity, which we'll see later, asymptotes, things like that, where we want to focus on those, not on these points that have nothing to do with the function. So that's just a little tiny thing, but you might have thought of thinking that at some point. You might have thought that at some point, so we're just not even going to consider points away from the function itself. So just stick to where the function's defined and very close to where the function's defined. All right, so let's check this out. We have an example here. So it says, consider the function f of x graphed to the right. Is f of x continuous at x equals -3? So let's just kind of look at this, right? Let's get our bearings. Looks like each grid line here is 1, so 1, so -1, -2, -3. So this number 1 is looking here. So maybe just kind of quick guess. Take a quick guess. What are you thinking? Just like gut reaction. Then what you do, and I was very sneaky, you bring this down here. I was ready for it. You bring your checklist in and you go through it. Number 1, is the function defined at -3? So for this one, to write it out, is this defined? Well, we go to our graph and it is. Yep. So number 1, check, because we're defined right at this point. This is equal to, looks like it's 1 for the vertical grid lines, -1, -2. All right, so this checks out. Awesome. Okay, what about the limit? Number 2, does the limit exist? So specifically, just to write it out, as we approach -3, what happens? Well, let's go from the left. We're approaching, we seem to be hitting -2. So from the left, remember that's that negative, I get -2. Okay, what about the right? As I approach -3 from the right, what happens? Well, let's do it. So I'm coming here, I'm coming here. What's my function doing? Oh, it's coming down, and it seems to be approaching 0 from the right. But what do we remember? If these are not equal, this does not exist. So the limit as x approaches -3 of our function does not exist. Okay? So what just happened, right? Let's think about this. What just happened? We went through the checklist that we need for continuity. Number 1 checked. Number 2, the limit did not exist. So, because the limit does not exist, so that's number 2 I'm talking about here, the limit existing. Because the limit does not exist, the function, you could write f of x too to make that shorter, is not continuous at x equals -3. There we go. So, what happened? We were looking for continuity. We went through the checklist. We messed up number 2. Didn't work. So we just say, because we didn't hit number 2, we wrote that out though, the limit not existing. We're not continuous at that point. All done. Okay, so let's try the second one. Is f of x continuous at 4? So let's change up our color here. Let's go blue. So let's go find x equals 4. So let's see, 1, 2, 3, 4. So here is x equals 4. Okay. So checklist, right? Let's just copy and paste this for maximum efficiency. Whoop, wrong one. Here we go. So, are we defined there? Well, we go look at 4. Yep, we are defined. So number 1, check. F of 4 is equal to 1. Okay, awesome. What about the limit, right? What's happening with the limit? We need the limit as x approaches 4, right, from the right. We need that to equal the limit as x approaches 4 from the left. Okay, so let's go look. Well, as I come in from the left here, it looks like I'm approaching 1, 2. As I come in from the right, I'm going down now, and I'm, okay, approaching 2. So, checks out, checks out. Functions defined, limit exists. All right, last stop. Is the limit the same as the function value? Well, let's see. The function value was 1, and the limit was 2. The limit and the function value do not exist. So we are discontinuous. Okay, so let's just write that out. The limit and function value are not equal at x equals 4. Thus, the function is discontinuous. Notice that I'm going to, specifically say discontinuous at x equals 4, because this function is continuous other places. So you don't just say the function's continuous or discontinuous, right? For now, we're saying the function's continuous at a specific x value, discontinuous at a specific x value. So you got to make sure that that's in your description, that you're telling me specifically what point you're talking about. All right, what about 8? Well, so let's do that in green. We'll do this one a little bit quicker. 4, 5, 6, 7, 8. So here, just to mark it with the green, is 8. Okay, that's right here. So quick. Am I defined? Looks like it. I had a point there. Check. Limit. Left and right, they look like they're going to the same value. I have no idea what this is, but doesn't matter. It looks like it's left and right approaching the same thing. Number 3, do those seem equal? They do. So all 3 of those check out, so we're continuous. So again, defined, check. Maybe I should get rid of that dot so you can actually see that there's a dot there, right? That's a little tricky. Okay, there we go. So we're defined, right? That's colored in. Check. Left and right approaching the same y value. Looks like it. Check. That y value we're approaching and the function itself, same value. Check. There you go. So f of x is continuous at x equals 8 since the function, again, you could just say f of x here if you want, is defined at x equals 8. The limit exists at x equals 8. And these values are equal. Ta-da! Continuous. Continuity. There you go. Okay, let's go down and talk now about why this function's discontinuous. Okay, so we have a graph here. This is a piecewise function, so something to kind of, just try to think through. And what you'll notice here is that if you just had this top piece, you plug in 1, what happens? This is not in the domain. 1 minus 1 is 0. You can't do that, so this function's clearly not defined at 1. So this piecewise is trying to plug the hole, because there's a hole here. Just this function has a hole at x equals 1. And so we could try to make it continuous by plugging in the hole. What happens? Well, based on the picture, we don't do a good job plugging in the hole. So just kind of based on this picture, we can kind of check this out. The limit as x approaches 1 seems to equal 0.5. Okay, so as I get closer and closer and closer to 1, it seems that this limit is getting closer, the function is getting closer and closer to 0.5, left and right. Okay, so we could get a little practice here. Why don't we just do a little quick practice to see, like, oh, how would I figure that out? Right? If I don't, if I didn't have this picture. Well, this is a rational function, so the first thought is, let's see if we can do some factoring. So let's just factor the top and bottom. X minus 1, x plus 1. And then we notice, oh yeah, okay, this looks familiar. Because we're doing the limit and not actually plugging in 1, I can cancel these two terms, right? And I end up getting x over x plus 1. Plug 1 in. So now plug 1 in into this. And we get 1 over 1 plus 1, which is equal to 1/2. 0.5. Okay, awesome. So the limit does work out to 0.5. This picture's not tricking us. That's really the limit. Okay, so awesome. Limit exists. That was number 2. Function is defined. So this little dot here is telling me that in my list, my checklist, number 1, this from the left and right and our work down here is telling me number 2. Check it. Limit exists. What's the problem? Number 3, limit needs to equal the function value. Well, what do we just see? The limit's 1/2, the function value is 1. This does not hold. There you go. So we broke the third one. Which hopefully you're starting to kind of see the idea of continuity, and that can start to kind of jump off the page to you. I see a limit, it looks existing, but the point needs to be right where that limit is, and instead the function is defined up here at 1 and not down here at the value 1/2. So discontinuous. There we go. And we had our checklist here that I forgot about. Okay, so those hopefully weren't too bad to do, just kind of graphically. And luckily, we have a ton to work with in terms of trying to figure out continuity. So what we're going to do when we're thinking about this, and actually this works, not just in continuity, but still these ideas were in limits, and they'll be later in the class too when we're doing things like derivatives, where we want to pay attention to how to combine or decompose functions and use what we know about the separate pieces. So what's this first theorem says? If f and g are continuous at some x value a, and c is just a number, 2 or 3 or pi, whatever, then the following are also continuous. So pay attention to this here. We've got f and g are separate functions that are continuous. We're assuming that the limit exists at a, the function's defined there, and those two things are equal. So we're assuming those three things about each of these functions. Then automatically, snap of the fingers, I know I add them continuous. Subtract, continuous. Multiply f by just some number, continuous. Multiply the two functions, continuous. Divide them and g's not 0, continuous. Just free. So this is telling me if f and g are continuous, this is important, these separately need to be continuous, then you can almost think of all of these combo functions. So combo functions, you get just free continuity out of these immediately. All right? So you should start to think like, okay, now maybe I see how more complicated functions, I could do this continuity idea and this limit idea still, just kind of in the background, because I can think of more complicated things as their smaller pieces. Very important idea. Often, complicated problems can be broken into smaller, easier, more manageable pieces. This is something that you always want to try to do whenever you're tackling any kind of problem. Can you break it into smaller pieces, right, that you're more comfortable with, that you know more things about? That's our goal with using this theorem. So you could think through some of these if you want to with the checklist, just like very quickly. F plus g, well, is it defined at a? Well, how do we define the sum of two functions? You just plug into each one. Well, f of a is defined because it's continuous. G of a is continuous, so it's defined, so the sum's defined. And the rest of them work very similar to that. Theorem 7 is also very useful because this gives us not only just a way to combine functions, it gives us this really big list of functions that are continuous in their domains. So what's super nice about this is, going forward, you see a polynomial, continuous at the domain. Just everywhere it's defined, continuous. Root functions, square root, cube root, if it's defined, just immediately continuous. So be a little careful, we're not comboing them yet. We're just thinking of square root x, cube root x, okay? Exponential functions, right? We're thinking of stuff like e to the x. I'm not composing this yet, right? We've got some of that up here and one below, but just like the base functions. Rational functions, trig, so you got your cosine, your sines, etc. And then, of course, stuff like log, base 10, natural log, etc. So all those where they are defined, this is important. You got to stay in the domain of the function, just immediately continuous. So you now have this huge toolbox of continuous functions. We've got a way to combine them to keep them continuous. And we even have another way to combine them to keep them continuous here. Okay? So Theorem 8 says if f is continuous at b and the limit as x approaches a of g of x is b, then I can compose. This is pretty neat. I can compose the two functions. Okay? And that limit works the way you would think it does. So the way you should think of this is, you got to be a little careful here because we're not actually talking about g being defined necessarily. This does not mention g of a equals b. But the limit existing means as you get close to a, g is getting closer and closer to b. And so this is not technically what this says, but the shorthand way you can kind of think of this is you've got f of g of x, right? So g, even if it's not true, right, we don't actually know about g of a. We don't know about this specifically. We don't need that for this theorem. But you can think of g kind of taking a and through g sending it to b, okay? And then f is going to take that to f of b. So all we're saying here is that comboing these functions, limits are cool with that, with the assumption f is continuous and this limit exists. And so what's super nice, and this is kind of, and the note makes note of this, is that if you have a limit and you're composing functions, which we're going to see in calculus constantly, under these conditions, so this is important, these conditions are important, under these conditions you can pass the limit through f in here. So I know that seems very abstract and weird, right? But this is the other way you got to think about things. How often have you seen functions where it's like the square root of, and then you've got something inside here? This is so common. You've seen so many functions like this, right? Cosine of a function, etc. All this is saying is that if I want to do the limit of these, I can take the limit and pass it through here. If I want to do the limit of this, instead of taking the limit of this crazy looking function, I can pass the limit in through, take the limit of the easier function, like the limit of a polynomial. We know how to do that. The limit of an exponential. That's not bad. Then, once you found that inner limit, this is going to be equal to some number. You just plug that into f and you're all done. So super, super nice idea. Very important idea. When you have this tool of being able to take an operation like a limit and move it through functions, oh, it just is crazy how many more problems you can solve because of that. So you're going to practice, this is going to become second nature, but we are going to talk through it when it's happening in the next example, just so you can kind of see where it comes up. But so constantly you're dealing with functions like this that this is going to be super helpful. This plus this toolbox of continuous functions plus this other way of comboing them, you can do continuity and limits for so many functions. So let's check it out. Let's go to an example. So explain why the function is continuous at every number in its domain. So we've got this function that is the combination of other functions. So let's just kind of start by identifying f and g. So I'm going to call f of x, x squared, and I'm going to call, we'll do blue, g of x, 2x, square root of 2x minus 1. So, why is this continuous? Well, let's think this through. I see a plus sign. Let's go back up here. I see a plus sign, right? What does this say? If the two separate functions are continuous at a, any point a, then their sum will be. So, oh, I have a sum. So what do I need? Why is this here? What do I need to show? I need to show, so what do I need? I need that this and this are continuous. If I can show these two separately are, then by Theorem 4, I know that f plus g is continuous. Right, so I get the sum if I can just get the two pieces, because that's what the theorem needed, the two pieces. Well, f is very easy. So let's start with that one. Let's do purple here. Let's start with this one. So f of x is a polynomial, right? X squared. By theorem, I'm going to forget the numbers. 7. it is continuous for every a in its domain. So hooray! Check. F of x is continuous. Done. It's a polynomial, so it's continuous. That's Theorem 7. Just use it. G of x, well, it's a little bit more. Let's think about g of x. I see a square root, so then this is a little tough. I know I go to the root functions. I'm like, oh, root function, I'm done. Not quite. This is not just square root x. It's square root 2x minus 1. Okay? So we got to do a little extra work here in that this g of x actually breaks up into two functions. Okay? So h of x is root x, which is the square root. That's in there, right? But then you also have another function, j of x, which is 2x minus 1. And so what is g? G is h of j of x. It's the combo. Okay? So g of x, just to kind of rewrite that equation, g of x is the combination of h and j. I plug j into h, I get g. Okay, so I've got that combo. But let's back up here a little bit. All right? This theorem says that if I'm thinking of this idea of continuity, right, specifically this limit, I need the limit to exist. That was one of the checks. Well, I'm looking at this function and I'm like, oh man, right? This g of x, let's go down here and let's do this maybe in red. Oh no, I like this color. This is a nice color. So I need g of x to be continuous. Let's just rewrite it, right? Okay, so how do I get this to be continuous? Well, I need what? I need g of a to be defined. Well, explain why this function is continuous at every number in its domain. I only care about where this function is defined. If this is defined, this r of x is defined, then so is g. This is kind of just a silly thing, but we'll say it anyway. I only care about where this is defined. The only way this is defined, this whole function, is if this piece is. So, easy check. But there's nothing crazy going on here. We got it. Well, number two, what do we need? We need the limit at any of these points, again, in the domain that we care about here. We need this to exist. Okay, but let's write that out. X approaches a of this function. Okay, now what do we know about this? Well, we already saw that it was a combination of two other functions, right? So how do we pass this limit in? Here's what we want to do. This would be really nice. The limit as x approaches a (3, 2, 1). Here's to be really nice. If we could take this limit and pass it in through the square root. Right? That would be really nice. Just take the limit of 2x minus 1. So can we do that? Well, let's go up. What does this say? It says if I have f of g, again, that's what we have here, right? I know I named them different functions, but the names don't matter. If I've got a combination of two functions, okay, got it, check. If that outside function's continuous, okay, at b, so square root, continuous. Well, the square root function is continuous. It's a root function. So square root of x is continuous at every number in the domain. So immediately, I know that that works. So by Theorem 8, I've got f, it's continuous. Okay, check. And the limit of g of x as I approach a equals b. So this 2x minus 1, I need this limit to exist. Okay, so think about this. As x approaches a, all right, 2x minus 1. Well, 2x minus 1, that's a polynomial. So of course this limit exists. So check. I've got that. So far, check, check. Then this says we can pass the limit through. So just to kind of write that out, why did we do this? So why we did this was the square root function is continuous on its domain. So again, square root, perfect. So wherever this is defined, square root is continuous. So we can, that's check. Also, so we got this. Also, we know that 2x minus 1 is a polynomial. So the limit as x approaches a, no matter what a is here, as long as it's in the domain of the function, which in this case it's a polynomial, so it is. This is a polynomial, so the limit exists. So we're good. So this limit exists inside. The square root function's continuous on its domain, so I can pass this limit through. All right, and so once passing that through, you're going to get, just plug it in because it's a polynomial, square root of 2a minus 1. But what's g of a? Well, g of a is, plug in, square root 2a minus 1. Oh. These are equal. So the function's defined because we're only talking about its domain, so of course it is. The limit exists, right? Because we're able to pass that limit through, we can do that calculation without too much trouble. And the value of the function and the limit are the same. So g of x is continuous. G of x is continuous. Okay, so let's go back up. By Theorem 4, since g and f are continuous, their sum is continuous. So finally, to just kind of wrap this up, we'll go back to blue. So to wrap this up, since f of x and g of x are continuous, our original function r, which is the sum of them, is also continuous. By Theorem 4. Ta-da! So I'm not going to ask you to go through in all of this detail and all of the citing, each of these theorems exactly to solve problems like this, to find continuity. But I just wanted to show you, where all the pieces kind of fit with those theorems into this. And what you're often going to do looking at this is be like, x squared, that's a polynomial continuous. Okay, square root, and then inside is a polynomial, continuous, continuous, add two continuous things, continuous. Done. Like that. That's the thought process that is going to happen when you're thinking through this. But just to kind of show you how to actually go through each piece of this, just so you can kind of see it. All right, so the last thing in this section, the intermediate value theorem. So this is just kind of a neat thing that comes from continuity that's, just nice to know and useful to build into a different theorem later that's even more useful. So what does this say? It says, suppose you have a function f that's continuous on a closed interval a to b, so two numbers, a to b, and let n be any number between f of a and f of b. So you could see that pictorially here. Here's f of a, here's f of b, n is just anything in between here, okay, where they're not equal. You'll see why we do that in a second. Then there exists some number between a and b such that the function, when you plug that number in, actually hits that y value. So the intermediate value theorem says, if your function starts down here and ends up here, then there had to be some point where you crossed this y value. That's it. Now, It could happen multiple times. See in part B, it could happen, you could hit it multiple times. You could only hit it one time. That's fine. But you have to have hit it at least once. That's it. Intermediate value theorem. Okay? So after you think about this a little bit, it might seem kind of silly, like, oh yeah, duh. Well, let's see kind of how useful it can be, because there's actually some pretty cool ways to use something that may seem kind of obvious. So let's check this. It says, use the intermediate value theorem to show that there is a root of the equation e to the x equals 3 minus 2x in the interval 0 to 1. So we can use the intermediate value theorem to show, in this example, that there is a root of this equation. So what are we really looking for here, right? We're basically just to, and I'm going to rearrange this a little bit. Minus 3 plus 2x equals 0. So what are we kind of saying here? We're saying we think that there is an x value I could plug into this, so this is root, such that I can make this whole thing 0. And that x value is inside 0 to 1. Okay, so let's go back to the intermediate value theorem. What does it say? It says, suppose f is continuous on the closed interval a to b. Okay, so our a to b here is 0 to 1. So 0 to 1. We want to be continuous. Well, this is a perfect practice example for what we just did. Why is this function continuous? So kind of step one. We need to show that this is continuous. Well, just going through it a little quicker than the last one. This we'll call g of x. That's a polynomial, right? And so Theorem 7 said this is continuous on its domain, which is every number. So definitely 0 to 1. Okay, well, that's good. What about this one? This is f of x, just to call it something. This is exponential. And again, we get the same thing here. Theorem 7 says it's continuous on its domain. And again, this is defined everywhere, so definitely 0 to 1. Then we combine these two facts. Right, we can combine these two. Theorem 4, we've got f plus g is continuous. So just to kind of like go through and practice thinking about this again, but we know now that this function's continuous on this interval, so we can keep reading. Let n be any number between f of a and f of b. Okay, so really step 2 then should be, if this is our function, right, what happens when I plug in 0 and 1? So let's just do it. E to the 0 minus 3 plus 2 to the times 0. That's negative 2. Okay, and then e when I plug in 1 minus 3 plus 2 times 1. That's equal to calculator time. Well, I guess we don't need one, right? So that's 2 minus 1, so that's 1.7 and some change. We'll actually use a calculator though. So that's e minus 1 is 1.718 and some change. Dot, dot, dot. Okay, so what is this telling me, this theorem? It says that this function is going to hit every single y value between negative 2 and 1.718. So we don't need to even know what this picture looks like, but we can draw this on a number line. Negative 2, 1.718, and some change. The intermediate value theorem says that this function here will hit every single number in here. Maybe more than once, who knows, but it's going to hit every number in there at least once. Well, we want a root of this equation, which means we really want to hit 0. That's our goal. Let's hit 0. So, How do we assure that we're going to hit 0? Well, let's let n equal 0. That's the number we want to hit, right? Go to our little number line here, and would you look at that? 0 is right about here. Woohoo! So the intermediate value theorem says that because 0 is between when I plug in 0 and 1, right? I plug 0 in, I get all the way at -2. I plug 1 in, I'm all the way up at 1.718. The intermediate value theorem says I had to have hit the y value of 0 at some point. So, just to write that out, since f of 0 is -2 and f of 1 is 1.718, the intermediate value theorem says there exists some c, we don't know what it is, between 0 and 1 such that e to the c minus 3 plus 2c equals 0. Boom. And there you go. So pretty powerful tool. Simple sounding. Oh, you hit some low point, you hit some high point, you're going to hit everything between because you're continuous. Oh, look at me, I'm so fancy. What a fancy theorem. But finding zeros of a function is actually a very nice and important thing to be able to do, and this tells us that we can. And so then later in the course, we'll be able to talk about, some fairly simple but still pretty powerful ways to find something like this using an approximation method, an algorithm. And so what this does, these combine, the intermediate value theorem can help us say, okay, where do I look for this? And then we can use an algorithm to help us try to find the C. Because again, this is non-constructive. It doesn't actually tell us where C is. It just tells us that it exists, which means we can go use another tool to find the C. But you got to think about this. You're trying to tell a computer to do something. If you're not even looking in the right place, you might be wasting a ton of time, computing power, or whatever. This theorem's helpful to tell you, okay, we're in the right place, now go look. Intermediate value theorem. All right, so that's all for this video. Make sure you're asking me questions, email, come in to see me, whatever you need. Keep studying hard, and I'll see you in the next video.